Can't believe it. April 1st. Here we are. Okay, we are recording. I am not on mute. All the usual check-in points. One thing I wanted to show you was on Moodle first. Where are we here? Oh yeah, this week. I don't have a pointer, so you'll just have to kind of guess where I'm pointing at. But so today we're doing section 9.1, and then on Monday we'll do section 9.2, and then that'll be it. And then we've got our lab exam at 10 on Moodle, and it's just a 50-minute Moodle quiz on Friday. Your assignment 9 is due on Thursday, April 9th, and then assignment 10 is due on Sunday, April 12th. So you've got a lot of time to do those. Assignment 9, you're able to do all of it now since we finished chapter 8 last day, but and I posted some stuff here. So there's the lab test review version 2. That's just a list of topics that that a colleague of mine prepared, and so I just kind of stole that. I also posted the test 2 solutions in case you're curious. And remember, you can access your test 2 through Gradescope. So if you're having trouble, then let me know. And then there's the practice lab exam and the practice lab exam solutions. I guess they should be in a different order. And today we're going through the chapter 9 notes. That's very poorly named, but whatever. So the chapter 9 notes I posted as well. Okay, so first off, any questions before we start here? Let's see here. So we're starting chapter 9. What's nice about chapter 9 is that we still use, we're still doing hypothesis testing, we're still doing confidence intervals, right? So in that sense, it hasn't changed. But what I'll do up here is I'll just say April 1st, 2020. And this is going to be part 1. And then part 2 will be section 9.2. So you've got your lab exam on Friday. Oops. On Friday, 50-minute Moodle quiz. At 10 o'clock. It's just going to be very quick, just kind of short answer style. Well, not short, it's multiple choice. But it'll be similar to that practice test. And also see practice lab exam and test number 1, multiple choice for review. And so we've already covered a lot of those questions in test 1. There were a couple more, like pick the appropriate null hypothesis, for example, or alternative hypothesis. Those would be new, right? But besides that, we've done them all before. Okay, so one thing that we haven't really talked about yet is categorical data, right? So far we've been talking about means, right? Oh, I got a question here. Oh yeah, so test 2, or sorry, do you want test 1 or test 2? Test 2, question mark? Because test 1 was handed back. And then test 2 is on grade scope. Let's see, I'll put that here. So test number 1 was handed back. And test number 2 is on grade scope. Email from grade scope. Okay, let's see here. Okay, nice. And I'll just double check, but I usually post the solutions. Put up in way back here. Yeah, so I posted the solutions to test 1 in the week 6 block of Moodle. So at least you've got the solutions. And I mean, you could just hide the solutions. Good. So, yeah, so the difference here is that we've been talking about the means, right? Because we've been talking about, so for the means is for numerical data. Now, we haven't really talked about proportions in terms of proportions from data, right? We've talked about proportions as if they're probabilities, right? And they are, but now, so proportions, let's take it out here. Proportion, so potentially, are from categorical data. So things like 4 out of 5 dentists, blah, 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 recommend whatever toothpaste they're advertising. Right, and so proportions are what we're going to be focusing on now. So proportions behave a little bit differently, right? Because proportions, they don't have a mean or a standard deviation, but that's okay, we can get by without it. So one thing that we've learned, right, is that we're going to have a population proportion, right? Just like we had a population mean mu, and then we're going to have a sample proportion, just like we had a sample mean x bar, right? And so the difference here is that we use the hat. Hat denotes the sample proportion. Unlike y hat, which is the predicted value of y, in regression, right? We've seen that hat, but depending on the context, right, the hat over a p denotes that it's a sample proportion, and then if we've got a y hat, it's the predicted value of y in regression. So it will be obvious, right? If you're in a regression setting, then the hat means a predicted value. If you're in just the categorical analysis setting, then the p hat, or anytime you've got a p underneath, it's going to be p hat, means that it's just a sample proportion. Here we go a little bit astray because we've got this p to represent our population proportion. And I'm pretty sure, let me grab your, or I can pull it up here, on your formula sheet, right? So now on your formula sheet, you're in this section of your formula sheet on the back side, right? And notice that we've used P for the population proportion. So what we said before was that we will always use Greek letters, right? For populations. We could use pi, but it can get confusing. And a lot of people do use pi, but it can get confusing because pi is is a number, right, or it's a constant. So that can get a little bit confusing. So here, this is one time we don't use Greek letters for the population parameter. Right. Unless you use pi, and that's fine too. So our null and alternative hypotheses have to be about the population parameter, right? So in this case, instead of talking about mu, right, our hypotheses are going to be about p or pi if you prefer, right? It's just a matter of preference. I'll be using p, but you can just as well use pi, and yeah. So same as before, right? Our goal is to figure out what the population proportion might look like, right? We're only able to collect a sample and calculate the sample proportion, but then we use that sample proportion to try to infer something about the population proportion. And so the sample proportion, okay, is going to be measuring some sort of success, right? And so that sounds familiar because it is, right? So think back to binomial, right? The binomial section, we talked about a success, failure, right? Those are categories. And so we're dealing with categorical data. So success, failure is categorical data. Okay, so the proportion, the sample proportion of successes is going to be p hat, which is the number of successes in the sample over the total number of individuals in the sample. So thinking back to our most basic, the one that we're all familiar with, right? 4 or 5 dentists agree that Colgate, whatever. And so 4 is the number of successes, right? The number of dentists that agree with the statement, and 5 is the total number of individuals in the sample. Most likely they didn't just talk to 5 dentists, right? But it can reduce to 4 out of 5, right? So we can reduce it to 4 out of 5. So just like before, right, we said our X bar, our sample mean, if we released our sample back into the population and we collected another sample, even if it's completely random and well collected, right, our sample mean would change. Same idea with the population or the sample proportion, right? The sample proportion, if we released our sample and we collected another sample of dentists, let's say, and ask them if they would recommend Crest or whatever, Sensodyne, no, never. Then we would get a slightly different sample proportion, right? And so the idea here is that we get a sampling distribution of a sample proportion. So one thing that's interesting about categorical data is proportions follow a normal distribution, which I know, crazy, but we have to check assumptions. So here, what I'll say is we haven't really focused on checking assumptions when analyzing means. But for proportions, it will be important, right? And so what we have to do is we have to check these assumptions, and it's just going to be a matter of memorizing these things, right? There's going to be quite a few things that we have to check, but what we'll do is we'll do some together, of course, and then it's just going to be a matter of just memorizing them and just blah on the page. So there's a little explanation on the side here why we have the sampling distribution. That's not really that important. I want to just dive into our assumptions. As a whole, there's only 2 assumptions, right? But they break into little subparts. And so first thing, we have to have independent observations. So the first way that we can do that is we pick a random sample. Okay, so we know that, but we have to make sure that we have a random sample. If it doesn't say in the question, then you have to state that as an assumption, right? So even if it doesn't say, then you say, we assume you have a random sample. We also tack on the 10% condition. So the 10% condition then says that, okay, well, your sample size has to be less than 10% of the population. And we've kind of talked about this briefly, right? Where the idea is, okay, if you're collecting a sample and you want independent observations, well, if you collect a sample that's a huge part of your population, right, more than 10% of your population, then you're more likely to have non-independent observations, right, or dependent observations. And so here, what this means is our sample can't be too big, right? It has to be less than 10% of the population. Now, usually, this is a matter of just arguing, oh yeah, 500 17-year-olds in the Okanagan, I don't know, is less than 10% of the 17-year-olds in the Okanagan, for example, right? We would just argue that it's reasonable, right? That our sample size isn't too big. So these 2 conditions, we just argue that these are satisfied, right? Or assumed, but you have to state them as assumptions, right? Even if it doesn't say, or even if it's not clear what the population size might be, right? Then you would say it's reasonable to assume that a sample size of whatever is less than 10% of the population of whatever you're talking about. Or you would say, I'm assuming that this sample size is less than 10% of the population. Right. So that's the independent condition. The normality condition changes depending on if we're doing a hypothesis test or a confidence interval, right? So you'll want to read the question and figure out which one you're doing. If you're doing both, then you can just go ahead and check both, okay? Right away when you're checking your assumptions. So how these questions are going to go is you're going to figure out what type of question you have. If it's a proportions question, then you have to check the assumptions. You read the question, you read the rest of the question, figure out if you're doing a hypothesis test or a confidence interval, and then depending on which one you're doing, you only have to check one of those. Or if you're doing a hypothesis test and a confidence interval, then you should just check them both right away. So if you're doing a hypothesis test, then you'll have a null hypothesis. And from your formula sheet, right, you'll see your formula sheet says that your null hypothesis is that P equals some P naught. This is the same setup as we had for one sample mean, right? We're testing one sample of proportions, or one sample proportion, against some hypothesized proportion. So what we do here is we take this hypothesized proportion and we calculate that the number of expected successes and failures, right? And so here, I'll make it easier. Q naught is 1 minus P naught, right? And so I usually just use P and Q. Q is just the opposite of P. So you'll see that in the notes, but there's also a little note here down here. So hopefully it's not too confusing. I didn't clean these up from when I had them last year. So usually I'm a little bit more, I don't know. I just use Q instead. I don't know what that makes me. Lazy? Maybe. So this is the expected number of successes and failures if the null hypothesis is true, right? But all you do in your calculation, and we've done these calculations for the binomial, right, is, okay, well, NP has to be more than 10 and NQ has to be more than 10, right? So this is the same as the binomial assumption. As the binomial, sorry, the normal approximation to the binomial assumptions, right? So we've seen that one before, and in fact, the whole reason that we're doing this is so that we can say that the proportions follow normal distribution. So it makes sense that because the binomial is a categorical test, right? So now we've got categorical data, so proportions, so there's going to be overlap in the assumptions. If you're doing a confidence interval, you don't necessarily have a null hypothesis. So a lot of people ask me, oh, well, how am I supposed to test this condition if I'm doing a confidence interval? Well, you don't. You test this one instead. So you have to have at least 10 observed successes and failures, meaning you take your n times the sample proportion, has to be more than 10, and n times your sample, I guess, non-proportion. Q hat is 1 minus P hat. Right, you can replace those Q's with 1 minus P. So depending on what you're doing, right, hypothesis test or a confidence interval, that's going to determine which assumptions you check. You always check the independent observations, right? Do you have a random sample and is your sample size less than 10% of the population? These things are going to be just a matter of memorization, right? So you're going to need to memorize these assumptions. Like that. That doesn't look very nice, does it? Oh. I can never do a curly bracket to the right. Anyways, there we go. All right. So we're going to memorize those assumptions. There's really nothing we can do about that. But once you've done enough of them, you will find a rhythm, right? And so just make sure that you're touching on all of these points, depending on if you're doing a hypothesis test or confidence interval. So what we're finding here, if we just have a look at your formula sheet, right, we've got a confidence interval. It uses P hat. We're back to Z star, which is kind of fun, right? Because we know how to find Z star, right? We can use the t-table, that Z star line at the bottom. We've got a P hat, 1 minus P hat, and we've got N. So what's nice about proportions is the only thing we really need is our sample proportion and our N. And remember, our sample proportion is the number of successes over N. So usually we only need the number of successes and our n in order to solve these problems. We can also solve for sample sizes. We're going to leave that for a little bit longer. Okay, and I want to just show you the hypothesis testing section for one sample proportion, and then next day we'll talk about the two sample proportions. Again, once we involve two samples, our formulas get quite a bit bigger, as we saw in testing for the means, but we can handle it. So we've got our null hypothesis is going to be that p equals some p naught. That p naught is the proportion that we want to compare our sample proportion to. Then what's pretty fun is we're back to a z-score, right? So instead of a t for proportions, we actually calculate z-scores. And our p hat is our sample proportion. Our p naught is our p from our null hypothesis. Same thing here, p naught is here, p naught is here, and then we need n. So again, not very much information that we need to solve these problems, right? We know how z behaves, we know how to find a p-value for z. So in that respect, it's really back to basics, right? We're back to z. We can find p-values for z. They behave the same way. It's just a different way of looking at things. So, like I said, it's the same as testing for one sample mean, right? There's going to be some hypothesized proportion p naught that you want to compare your sample proportion to. And so again, we could have a two-sided test like this, or we could have a one-sided test, or a two-sided, or another one-sided test less than or greater than. It just depends on the question that you're testing. Step 2 in your hypothesis test is going to be, okay, well, we can kind of ignore this. This is true, but we can ignore it. So we can calculate the z-score. Right, we've got our sample proportion minus our hypothesized proportion, and then here, right, instead of q naught, even though I think it makes it look nicer, people don't tend to like it that much, and by people I mean students. Q naught is 1 minus p naught. So once we have a z, right, then we're back to z tables and we can find the p-value. And so here, what's important is that your z, your calculated z, might be up here, right? This area is your one-sided p-value. If you need a two-sided p-value, right, then you would replicate that over here, right? So the two-sided p-value is the one-sided p-value times 2. Okay, so that's important, right? So because it's a little bit harder, well, not harder, but it's that extra step. If you need a two-sided p-value for a proportions test, right, if you've got a z, then you need to remember to multiply your one-sided p-value by 2. Right, you're going to find your one-sided p-value, but then you have to multiply it by 2. Once you have your p-value, right, then your conclusion stays the same. If the p-value is less than the alpha level, whatever it is, usually 0.05, we have enough evidence to reject H0 in favor of HA. Right? If the p-value is not less than the alpha level, we do not have enough evidence to reject H0. And so here, if it is less, then we have enough. If it is not less, we do not have enough. Right? And so I use that phrasing just because it's easier to remember. Okay, if the p-value is less than the alpha level, then we have enough evidence to reject H0. Remember, you always do your rejection in terms of H0. And if you never mention HA, that's fine, right? usually I say if I'm rejecting H0, then I'm gonna say in favor of HA. But if we don't have enough evidence to reject H0, end of story, right? There's nothing going on here. There's nothing we can do. Okay, I'm gonna check for questions. So if you have any questions, let me know. Question? No? Oh, Gagandeep, did you have a question? No? Should I, you're just, should I mute you? Or did you have a question? There. If you have a question, then just unmute yourself. Or type it in, but it might take a while. All right, so no questions. I think we should do an example then. All right, so what I have done, well, I mean, I like to mix things up. You guys got a pretty boring test too, because it was so out of the blue and whatever. But you did it, so I'm glad. But sometimes what I do is I have test 2, which covers one sample mean sigma known, one sample mean sigma unknown, matched pairs, and then 2 independent sample means. So what I do is everyone selects 2 of the 4. So all 4 questions are on the test, and then you pick the 2 that you want to do. And it's just kind of a fun thing for me to see which question types people choose, but also, I mean, it just makes you, because those questions would just have been introduced, and so it's hard to study all of them, but as long as you're able to identify which types of questions you have, and you're able to do those, then it's just kind of a fun experiment that I do. Not really an experiment though, because, well, it's not. But anyway, so they're given a choice from 4 types of questions, right? So these are all means questions that we've covered. And so this was chapter 7, and then 8.1, 8.2, and 8.3. And they each selected 2 of the 4 questions to complete. And so 25 people chose the sigma known, 48 people chose the paired t-test, right? So the paired samples. 40 people chose the 2 sample means, so the 2 independent means, and then sigma unknown, sigma known or sigma unknown, right? That's the 1 sample t-test. I'm always surprised by very few people tend to choose the sigma known, right? Because that's where we started. And so I'm always kind of surprised by that. But I guess by that point, people tend to be more comfortable with t-tests, right? And so here, these are t-tests. And this is the z-test. So a total of 78 students. So this is just me kind of outlining how we should do this analysis, because it's tricky because there's 78 students who wrote the test and they chose 2 questions. So a total of 156 questions were chosen. And so it might be easier to consider the sample proportions of the question types chosen, right? And so 16% or 0.16% chose the sigma known, 30.8 chose the matched pairs, 25.6 chose the 2 independent means, 2 independent sample means, and then sigma unknown, 27.6. And so here, looking at this, it looks like the paired data question might be the favorite, right? And so here, right? So the question that we're going to analyze is there evidence? This is a dead giveaway that I have to do a hypothesis test. That paired data is the preferred question type. Are the assumptions for inference satisfied? So here, this is where I remind you to check the conditions or check the assumptions for proportions. Right? We've already identified that we're doing a hypothesis test, so there's no need to check the assumptions for confidence intervals. No need to check assumptions for CI's confidence intervals, since we are only asked to do a hypothesis test, right? Remember, going back to those assumptions, right at the top of the page here, or the top of the document, depending on if we do a hypothesis test or a confidence interval, that's going to dictate which conditions to check, right? And so here, when we're asked to do a hypothesis test and are the assumptions for inference satisfied, right? We don't need to check the conditions for confidence intervals, right? Because we're only doing a hypothesis test. So, because there are 4 question types, if there's no preference for a specific type, the proportions for each will not be significantly different from 0.25, right? So a quarter should have chosen sigma known, sigma unknown, paired, and then 2 independent samples. So our null hypothesis is going to be that p equals 0.25, right? And so we're assuming, so here what we're saying is assuming all question types are equally likely to be chosen, because that's how we do these null hypotheses, is we assume that there's nothing going on, and then our alternative hypothesis says, well, you know, if we find that this is unlikely, then what's our alternative hypothesis? What else do we think is going on here? And so here, I'm introducing a step 0 where we check the assumptions. This is only for proportions questions, right? We should be checking assumptions for t-tests as well, but I don't focus on that because we usually just ram it through anyways. So yeah, so I don't bother, but it is important for proportions questions. So the first thing we have to check is, do we have independent observations? So remember, there's 2 things that we argue. Do we have a random sample? So what we're saying, it doesn't say explicitly that these 78 students were selected at random, but we will assume that the sample of 78 students is a random sample of all students taking statistics in the winter term of 2018-2019. So this was last year. That's not necessarily accurate, but it is what we're assuming, right? And so we have to let go of, you know, well, that's not necessarily true. We're saying, okay, here's an assumption that we're assuming, right? And so same thing with the 10% condition. We will assume that a sample size of 78 is less than 10% of the population of statistics students, right, at Okanagan College, presumably in the winter term of 2018-2019. Whether that's accurate or not, right, we don't really know, but it is something that we're assuming, right? And so here, since we're doing a hypothesis test, right, and remember we said that P naught, we're going to replace it with 0.25, then our conditions that we check, and again, Q naught is 1 minus P naught. So here, the conditions that we check is that NP naught, the hypothesized P, must be less than, or sorry, greater than 10. So 19.5 is more than 10. So that's good, that checks out. 58.5 is more than 10, right? And so the assumptions for inference are satisfied. We've already done a version of this, right? So I'm not too concerned about explaining that again because we did that in the binomial setting. Okay. Here, we had 4 categories, right? But what we're doing is we're breaking this up into a success is if they chose the paired test, and a failure is all others, right? If they didn't choose a paired test, right, for their question. So we can find our sample proportion, right? And just ignore the code here. We're not using R, so you can just ignore it. But the sample proportion that we found earlier was 0.3076923. This, I'm going to round to 3 decimal places just because I want to capture that 0.08 or 0.308 at least. Ideally, I would use all of these, but it just gets a little bit out of hand. So 3 decimal places might be good. And so our p hat, right, this is our sample proportion. P hat is the sample proportion. We're trying to learn something about p, the population proportion, right? So from 0.308, is 0.308 significantly different from 0.25, right? So our null hypothesis we already determined was p is 0.25, and if the paired test is the preferred test, then this is a one-sided test since we want to know if paired is the preferred question type. Oops. Right? So if it's more than 0.25, right, then we don't have this even distribution anymore, making the paired the preferred question type. Okay, and so what we do, right, we've got this one-sided test, and so now we can do the test. So we calculate our Z, which is our sample proportion minus our hypothesized proportion, remembering that Q naught is 1 minus P naught. That's on your formula sheet, right? I just don't want you to get confused when you're reading my notes because I didn't swap them out, but it should be okay. Remember, all we need is a P hat. That's our sample proportion, 0.308. How far is it from 0.25, right? Which is our hypothesized proportion. And then we use our hypothesized proportion down in the square root as well. And our overall sample size was 156. So we end up at a Z. Remember, this is a Z. Z goes to 2 decimal places because we have to match the Z table, right? So unlike the T table where we use 3 decimal places, so Z, 2 decimal places, 0.67. So 1.67. This is not beyond 2, right? Remember, we still use 2 as kind of a guideline, right? We suspect that we're not going to be able to reject the null hypothesis, okay? And so here, we suspect that we will not be able to reject H naught. It's kind of close, 1.67, to reject H naught, just because it's not past 2, right? And so, but we're going to use our p-value to be the judge, right? So we've got a z-score, so now we use the z-table, and what we've got, right, is we've got our normal distribution. Z is centered on 0. We've got a Z of 1.67. The p-value is always the area in the tail. So this is our one-sided p-value that we have to find. So our one-sided p-value, well, the area to the left is 0.9525. So the area to the right is, oh man, ignore that one. Nope, that's not it either. Ignore that one. 0.0475, there. So the one-sided p-value, just focus on this one, without the typo, is 0.0475. One thing that I will say, this 0.0475 is less than our alpha level, right? And we needed a one-sided p-value because we had a one-sided test. This is less than our alpha level, but it's pretty close to 0.05, right? And so here, I've just got a little note here. Be careful with p-values on the cusp of the alpha level, right? So when they're hanging out close to the alpha level, if there are consequences to rejecting H naught, right? So if you just use this and reject H naught and you submit your report and then 400 people get fired, that would be very bad, right? Because here, this was not a lot of evidence against H naught. It was enough, but it wasn't a lot, right? And so in our case for this question, does it matter? No, not really. Oh, a paired samples t-test is the preferred question type. Yeah, saying that, or it wasn't, then there's no harm done, right? And so here in this example, rejecting H naught is inconsequential, so we will go ahead and just base it off of the p-value. But just keep that in mind. You don't want to be rejecting things willy-nilly if you're so close to the alpha level. So here, if we had a two-sided test, right, our p-value would be 0.0950, right, this times 2, which means we wouldn't reject H naught. And so the two-sided test makes it harder to reject H naught, and that's why it's the default, right? And so it's only if we suspect that something particular is going on that we would use one-sided tests, which we do in this case. So we do not need to use R using, well, I guess we already found it with the Z table. So here you can ignore this. Ignore and ignore. And ignore. Just because we're not using R. So we have our p-value, so we jump straight from our p-value. Our one-sided p-value is 0.0475. Now we're ready to state our conclusion. So since our one-sided p-value of 0.0475 is less than our assumed alpha level of 0.05, we have enough evidence to reject H naught in favor of HA. Therefore, there is evidence that paired data is the preferred question type. Done. Okay. Here, right, in the next example, we do the exact same thing, except now only 25 people chose to do a one sample mean with sigma known out of a total of 156 questions. So again, we can compare it to 0.25 to figure out if sigma known is the least popular type of question, or if it's just maybe not that close to 0.25, maybe it's, or we want to know if the proportion, sorry, I'm stumbling over my words here, 25 over 156 was 16%, right? And so here, oops, 25 over 156 is roughly 16%, right? What we're asking here is 16% significantly less than 25%, right? Same question, just with a different proportion, and now we want to know if it's less than 25%. So what I actually want to do, because I know I'm kind of pushing it for time here, I want to talk about the confidence intervals, but also how to calculate the sample size that we would need, right? If you go to your formula sheet, there's also this sample size calculation that I want to introduce. And so we did sort of an example, we didn't write it out, of the hypothesis testing for one sample proportion. Now I want to talk about the confidence interval for one sample proportion, and then I really want to get to the sample size calculation as well. So, but as before, I'll just sneak in the solutions to this one here. So definitely work through it on your own, and then I'll put the solutions in. Maybe I'll put them, where can I put them here? Add a page. Example 2 solutions. Right, so I'll post those if we don't have time to go through them. So for the confidence interval, right, we already looked at it. We know what p hat is. P hat is the sample proportion. Z star, we already know how to find Z star. We're going to use the t-table because it's the easiest. And I'll erase all this. Whee. Yeah. So if you want a 95% confidence interval, right, then you scroll down all the way down to the Z star row, and this is where you find your Z star. So Z star from Z star row on the t-table. Right. And again, of course, Q hat is 1 minus P hat. Okay. Remember that P hat is the number, oh, I should make more room for myself here. Number of successes over n, right? And so technically, the only information that you would need is the number of successes and n, because then we're able to find P hat, we have n, and then we just need our Z star. So the only information we need is the number of successes and n, which is nice because if you're doing means questions, right, you need to know the mean, the standard deviation, your sample size, right? And so there's a lot more going on. Whereas here, we've really boiled it down to the number of successes and your total sample size. So we have to interpret the confidence interval. We need to remember that we're talking about the proportion, right? We're building it around a sample proportion. We're trying to capture the population proportion. So here, so on a test where students had a choice of questions, 48 out of 78 students chose to do a paired data question. So here it's a little bit different, right? Because I'm not looking between the the different question types, I'm just saying, hey, 48 out of 78 students chose to do the paired data question. And so 48 over 78 is going to be 61.5%, right? So our proportion is going to be different because we're just talking about 48 out of 78 students chose to do the paired data, as opposed to 48 out of 156 questions answered were paired data questions. So it just depends on what we're talking about. So construct a 95% confidence interval for the true proportion of students who would choose to do a paired data question. Choose. Wrong. So, question? Maybe? No. All right. Good way to get my attention though. Just turn your mic on briefly. Is anybody out there? So we can do a confidence interval for the true proportion of students who would choose to do a paired data question, right? And so our proportion, our sample proportion is 48 out of 78. And if we go to the solution here on the next page, right, we've got our p hat, which is our sample proportion, 0.6154, right, is what I'm going to use. We could use 3 decimal places, but here, as many as you can keep is good. So we have to check our assumptions. Remember that we're just doing a confidence interval, and so we need to check that our observed successes and failures are more than 10. But first we have to talk about our independent observations. So we will assume that the sample of 78 students is a random sample of all students, blah, blah, blah. Again, we're just stating that this is what we're assuming. These independent conditions are going to be the same as for hypothesis testing. So same as for hypothesis testing. So here, again, we're just going to say, we'll assume that 78 is less than 10% of the population of statistics students at the college in the winter term of 2018-2019. So now we need to check that we have at least 10 observed successes and failures. We know we had 48 successes. You can do it using the calculation, but it might be easier to just go for the numbers, right? The number of successes, the number of failures then must be 30, both of which are greater than 10. So these both check out. One thing to remember about these conditions when we're checking them, they will always check out, right? So if you're finding that they're not going to work, you're probably doing it wrong. It's not a matter of actually checking to confirm if we can continue. It's more about jumping through the hoops of checking these assumptions. But for our problems, all of these, we will just argue that they will always work. So then we can say that the assumptions for inference are satisfied. So now what we can do is we can go ahead and build our confidence interval. So if we need a 95% confidence interval, then we need a Z star of 1.96, and that's from our t-table. We build it around our sample proportion, right? And then, so our sample proportion p hat, q hat, again, q hat is 1 minus p hat. And so what we find is that we've got a margin of error of 0.1079673. So if we do find the interval, right, 0.6154 minus this, 0.6154 plus this, we find that roughly 0.5074 and 0.7234 is our upper bound, our lower bound and our upper bound respectively. We can convert these to percentages if we prefer, right? 50.7% to 72.3%, right? But we are talking about the proportions, so proportions should be in decimals, so decimals between 0 and 1. And so we're 95% confident that the interval from, so here, same blurb as always, right? So we're 95% confident that the interval from the lower bound 0.5074 to the upper bound 0.7234 captures the true proportion. And then here we just say whatever we were asked to build an interval about. The true proportion of students who would choose to do a paired data question. Okay. And so obviously I just copied and pasted here as an answer, right? So here, what's important is that because we're talking about proportions, these have to be proportions, right? Whereas we could use 50.74% to 72.34%, right? But these are not proportions, right? They are percentages. Oops. They are percentages. So you have to be really careful when you're talking about proportions. You don't want to convert them to percentages because they're different, right? So if you wanted to, you could say we're 95% confident that the interval from 50.74% to 72.34% captures the true percentage of students who would choose to do a paired data question, right? And so, but you'd have to change this to percentage if you've changed these to percentages. Otherwise, it just doesn't make sense. Okay. So there's another unrelated example, which might be nice, where I get you to do the confidence interval, and then also in part B, I get you to do sort of a hypothesis test using the confidence interval, right, which we've done before. So according to a 2012 Bank of Montreal RSP study of 1,000 Canadians 18 years of age or older, 67% of Canadians have a registered retirement savings plan RRSP. A Statistics Canada study reported that in 1999, 57% of Canadians had an RRSP, right? So here, we're assuming that this 57% can be considered the population proportion, right? Because it's from StatsCan. So we're going to construct a 90% confidence interval for the proportion of Canadian adults who have invested in an RRSP based on the survey, right? So based on this survey of 1,000 Canadians, they found a sample proportion of 0.67. So we're going to build a confidence interval, 90% confidence interval around that 0.67. Then, does this provide evidence of a change from 1999, right? A change from 0.57 in investing among Canadians, right? Because we're only interested in a change, our null hypothesis should be, or our alternative hypothesis, sorry, should be that it's not equal to 0.57, right? And then use your confidence interval to test the hypothesis. So again, let's leave that for a little bit and make sure that you check assumptions. Also check assumptions. Right, and because we're doing sort of a hypothesis test, confidence interval and hypothesis test, so you can check both of those conditions just to get used to checking both at the same time. Okay. All right, so like I said, until I've covered all this stuff up until 9.2, I'm going to have to just post the solutions to those examples later. let's see here. Yeah, there might be enough to do example 4 just on this blank page. Or I'll add a page. Okay, so just like we did in the Z situation with the a means question with sigma known, right? We can do a sample size calculation. So we have to have some desired margin of error M, and we need to know the desired confidence level of our estimates. And so we can solve for N using our margin of error, right? Our margin of error from our confidence interval is Z star times the square root of P hat times 1 minus P hat over N. So what we find is that, okay, well, if we kind of solve this thing for N, we find that we get Z star over M squared times P hat Q hat. Okay. If we go to the formula sheet, right? This is from the formula sheet, and I'll just copy it in here. Okay. From the formula sheet, notice that we're talking about P star Q star, or P star 1 minus P star. That's because, and then here we're talking about P hat Q hat, where Q hat is 1 minus P hat, of course. One thing to notice, right, is the difference between these two, right? Here I'm talking about P hat, here I'm talking about P star. And the reason for this is because this requires that we know P hat, which is fine if we've already collected a sample and we want to improve our estimate. That's not going to be the case often, right? So if we're organizing a study, so this is before we go out and collect any data, we're trying to figure out what sample size we need. It's kind of weird to think that we would have some sample size in mind. So we're not going to know anything about the sample proportion, so that's why we use P star and then 1 minus P star. And P star is the sample proportion, P hat if you know it, right? Or P star is 0.5, so we assume a 50-50 split if we have no preliminary data, right? So if you've collected a sample previously and you have some P hat, right, then you can use that P hat. But if you don't know anything about how this proportion is going to behave, then you can use P star as 0.5. And then I've just got a note here that using P star of 0.5, right, so if P star is 0.5, then 0.5, then 1 minus P star is also 0.5. So therefore, we assume a 50-50 split, we can call it, in successes and failures. Okay. And the reason we do that is because it gives us the most conservative estimate of the sample size required, right? So this will give us the largest N possible to satisfy those conditions. Okay, so here's an example. On a test where students had a choice of questions, 48 out of 78 students chose to do a paired data question. So construct a 95% confidence interval for the true proportion of students who would choose to do a paired data question. So we found this interval, right? And we found this margin of error. So here, this is our margin of error. Margin of error, M, right? Which we've rounded to 0.1080 or 10.8%. So what if we wanted to reduce the margin of error to 0.07, right? So from 0.108 to 0.07. So we want to reduce it by roughly 3%, roughly. Determine the sample size required using the sample proportion as preliminary data. So now we're saying, okay, well, we're going to use the sample proportion of 0.6154 as our preliminary data. Then part B, determine the sample size required assuming you have no preliminary data, right? So here we already have a sample size, a sample proportion. So we can use that, right? So here, what we're saying is that P star, we can use P hat, which is 0.6154. Here, we're saying, okay, well, we have no preliminary data. We haven't collected any information on this before, so we're going to use 0.5. So for part A, we would find that we would need a sample size of 186. And again, just like before, right, we've got our Z star, we've got our desired margin of error, we've got our P star, which in this case, we're going to use the sample proportion and 1 minus the sample proportion. Go through, solve this. We always have to round, right? Always round up for n, right, up to the nearest whole number, 186 in this case. And so, whereas if we used 0.5, right, assuming that we don't know anything about the sample proportion, and again, we're going to use a 95% confidence interval and a margin of error 0.07. So these things stay the same. The only things that are changing is the P star, which we're now using 0.5 and 0.5. What we'll find, there's no rounding needed because we land on a whole number, 196, right? Here, 196 is a larger sample size, not that much larger than 186. Right? Notice that this is a more conservative estimate, right? So here we're saying, okay, if we want to play it safe and we're pretending to not know anything about the data, then we're going to use a P star of 0.5. Right. So here, yeah, so we got a sample size of 196, and the difference between collecting 186 and 196, I would argue that you should always just use the more conservative estimate, but it's just introducing you to the two different ways. So if we want to estimate the proportion P with 95% confidence and a margin of error no greater than 3%, what sample size will be required? So here, this is a very general question. Very general question, right? Because we're just saying, okay, what if we want to estimate some proportion P, any proportion P, we don't know anything about it. For 95% confidence, I know Z star is 1.960. You can use the t-table to confirm. And I'm saying I want a margin of error no greater than 3%, which is 0.03. So then we want to find n, right? I'm going to use P star as 0.5 because no information is given. Okay. So we've got n is Z star over M squared times P star times 1 minus P star. Let me just make sure it is 2. I'll just put it over here. So in my case, I've got Z star 1.960 divided by 0.03, making sure that you divide that 3% into a proportion, times 0.5 times 0.5. And because I want to save that next page for the fresh page for next day, and I don't need that much room. I do 1.96 divided by 0.03, square that, times 0.5 times 0.5. I'm finding roughly 1067.111. So I would need n equal to 1068. This is regardless of whatever I'm talking about, right? If I just want to estimate some proportion with 95% confidence and I want to force my margin of error to be no greater than 3%, I would need a sample size of 1068, right? Doesn't matter what I'm talking about, as long as I'm measuring a categorical outcome, this is the sample size that I would need to satisfy this criteria, right? And so here, I'll just put it in. There's our answer. Okay. All right. So I think what we'll do, because there's definitely no time to do any other questions completely, what I'll do is I'll check for questions in the chat, but otherwise I'll just post the solutions to the confidence interval question and the hypothesis testing question. Yeah, these ones. And then next day, or I guess that's on, oh shoot, it's on Monday. On Monday, we'll finish all our material by doing 9.2. Remember, you've got your lab exam on Friday. It's going to be a 50-minute Moodle quiz at 10 o'clock. And so you'll just have 50 minutes to do it. It'll start at 10. And make sure that you have a look at the practice lab exam and the test 1 multiple choice. All right, I'll check for questions now. I'm seeing none. All right. So let me know if you have any questions after, but otherwise, we're all done and I'll boot you out. Okay. All right. See you later. And I'll see you in a bit, Manuel.
Okay.
See you, Sky.